Hello everyone. So this is the second hour of heat transfer, and in this hour we are going to talk about radiation and Newton's law of cooling. Here the most important topic which I will say you have to put 100% attention in radiation is the Wien's displacement law. That how does the lambda max of the spectral line shift with the change in temperature, because question from Wien's displacement law comes in NEET every year. So without wasting time, let's start learning the topic of radiation. So when I talked about little bit in radiation in the last hour, I said that every object above 0 Kelvin radiates. So every object above 0 Kelvin radiates EM waves. Now sir, what are EM waves? Electromagnetic waves. Now electromagnetic waves have a big spectrum. So there are radio waves, there are microwaves, there is infrared, there is visible, and then there is ultraviolet, there is X-ray, and then there is gamma ray. Out of the entire spectrum of the EM wave, our eyes can see only a small part which is called visible. Going from left to right in the entire spectrum of EM waves, we can see that the energy increases. From E equals to SC by lambda, going from left to right, the energy increases, so the lambda decreases. And from E equals to HF, we can say going from left to right, since the energy increases, we can say that the frequency increases. So radio has the least energy, higher than that micro, higher than that infrared, higher than that visible, and so on. Now sir, our body is also above 0 Kelvin. So are we radiating? Yes. But most of the radiation produced by human body lies in the infrared region. Now let's say there are two human beings in a room and the light source is not at all present. One human being can't see other because of the absence of visible radiation. The human body radiates out infrared radiation, but a human eye can't detect infrared radiation. That's why we can't see each other, given that there is no third external light source giving out visible light. Heat transfer due to radiation can take place even in vacuum. Sir, why can the heat transfer due to radiation take place even in vacuum? Because beta, the radiation mode of heat transfer is because of EM waves, and electromagnetic waves can travel in vacuum. They travel from sun and reach earth, so they can travel in vacuum. Moreover, one more point I will like to explain here. Electromagnetic waves travel at speed of light, right? So this is asked, which is the fastest mode of heat transfer? So you will say radiation is the fastest mode of heat transfer, because radiation can travel from sun to earth, and sun is far away from us in the form of EM waves. So radiation can travel in vacuum, and radiation is the fastest mode of heat transfer because radiation is nothing but EM wave. So now let's say we have got some random object and we are making radiation of energy Q to fall on it. We are making photons of energy Q to fall on it. What happens when some energy falls on the object? Three things can happen. It can reflect the energy, it can absorb the energy, or it can transmit the energy. Most of the substance do everything little. So they reflect little bit of the photons incident, EM wave incident, the radiation incident. They absorb some part of it and then they transmit some part of it. From the principle of conservation of energy, we can say the total energy incident equals to the sum of energy reflected plus energy absorbed plus energy transmitted. So the total energy incident Q equals to energy reflected plus energy absorbed plus energy transmitted. Sir, why for energy you are using the symbol Q? Because beta, Q represents heat, and here we are learning the radiative mode of heat transfer. Heat is nothing but energy in transit, but since we are talking about heat, rather than using term EEE, we are using QQQ. Now beta, if we divide each term by Q, that is the total energy incident, what we will get? 1 equals to QR by Q plus QA by Q plus QT by Q. Now what does QR by Q represent? QR by Q represent the fraction of the incident energy which is reflected. QR by Q represent the fraction of the incident energy which is reflected. QA by Q represent the fraction of the incident energy which is absorbed. QT by Q represent the fraction of the incident energy which is transmitted. Now बच्चों, QR by Q has a name of its own. The fraction of the incident energy which is reflected is called reflectivity. Similarly, the fraction of the incident energy which is absorbed is called absorptivity, and the fraction of the incident energy which is transmitted is called transmittivity. So we say reflectivity plus absorptivity plus transmittivity equals to 1 for any object. Reflectivity, the fraction of the incident energy that is reflected, plus absorptivity, the fraction of the incident energy that is absorbed, plus transmittivity, the fraction of the incident energy which is transmitted, has to be equal to 1. Now, why do we see different colors of different objects? Let's say we place an object in white light. So what is white light? White light is the mixture of entire visible spectrum. So when I say white light, think of it, you have got entire VIBGYOR, all the radiation of different wavelength combined into one falling on the object. And let's say this white light falls on a leaf, a green object. Why does the leaf appear green? So because of the presence of chlorophyll. No. I'm not going there. We are talking about radiation here. So why does the leaf appear green? Because when white light falls on it, it absorbs some part of the spectrum, some wavelength, and it reflects some other wavelength. The mixture of all these reflected waves appear to be green. That's why we say leaves are green. Similarly, if we have got a red object, we see it, we say that, okay, this object is red. Why? Because when white light falls on it, entire VIBGYOR, all the possible radiation that can be detected by human eye falls on it. It absorbs some of them and it reflects some of them. Now, the combination of all these reflected waves appear to be red. That's why some appear, when placed in white light, appear to be red. So, sir, why does an object appear black? When you close your eyes and no radiation is entering inside your eye, what you see is black color. You see nothing. So the absence of all the visible radiation is black color. So if white light falls on an object and it absorbs all the visible radiation and reflects back nothing, then to an observer, no radiation comes inside their eye coming out of this object, and then this object appears to be black, the absence of EM wave. So my shirt and my hair are doing this thing. When white lights fall on them, they absorb the entire visible radiation and reflect nothing. That's why they appear to be black. Now beta, if you have got an ideal absorber which absorbs 100% of the radiation falling on it, such an ideal absorber will be called an ideal black body. So for perfect absorber, which are also called black body, they absorb 100% of the radiation falling on it. They reflect nothing, they transmit nothing. Since they reflect nothing, they transmit nothing, we say that for such object the reflectivity is 0, the transmittivity is 0, and hence the absorptivity is 1. So for perfect absorber, the absorptivity will be 1, while the reflectivity and the transmittivity will be 0. Next, for perfect transmitter, sir, what should I think of a transmitter? Glass. Visualize the glass I am wearing. If you have got glass, when white light falls on it, it lets majority of it to pass. It transmits. Okay, it reflects very less. It absorbs very less. So if you have a perfect transmitter, it reflects nothing, absorbs nothing. It transmits 100% of the radiation falling on it. So for such an object, you say that transmittivity is 1, while the absorptivity and reflectivity is 0. And then if you have an ideal reflector, like a mirror, if you have a mirror, then a mirror reflects, right? So for a mirror, reflectivity is very high, while absorptivity and transmittivity is very less. So for perfect reflector, you will say reflectivity is 1, while absorptivity and transmittivity will be 0. So now we should focus on discussing what is a black body. Sir, a black body is a body which absorbs the radiation falling on it. An ideal black body absorbs all the radiation falling on it. So an ideal black body absorbs all the radiation falling on it. I ask you a question. Is my shirt black? Yes. Is my shirt ideal black body? Can't say. Why you can't say? Because, sir, see, if you are wearing this shirt and this is appearing to be black, it appears black because when visible light falls on it, It absorbs all the visible radiation. So none of the visible radiations are reflected. Now we can't see other radiation apart from visible, but let's say some other animal or device can see. If let's say we are making infrared radiation to fall on your shirt, can you say with 100% guarantee that the infrared radiations will be absorbed as well? No, maybe the infrared radiation might get reflected. What is an ideal black body? An ideal black body is the body which absorbs all the radiation falling on it. So whether it's infrared or X-ray or ultraviolet, any god damn it type of radiation, it is going to absorb all of them. So for an ideal black body, we say that the absorptivity is 1, while the reflectivity and transmittivity are going to be 0. This is the case for ideal black body. Now, how do we create a black body in lab? Because ideal black body does not exist. So how do we create an ideal black body to study it inside a lab? So we have got a device that's called Fairy's black body. What he did was, he took a clay pot, completely closed, made a small hole into it so that through this small hole light can enter. Then he placed the darkest color known at that time. The darkest color means the best absorber known at that time, which is carbon black, also called coke, on the inner layer of this pot. So he took a clay pot, made a small hole, coated the inner layer with carbon black, which is the best absorber known at that time, and then he placed a small mirror opposite to the opening. Now what happens when some radiation enters through this hole? They get reflected from the mirror and they keep on bouncing within the pot and they can't escape. So as if this object have absorbed all the radiation coming through this small hole. So if some radiation enters, it just keeps on bouncing here and there and it can't escape. So we say that this small opening acts like an ideal black body. Irrespective of the type of radiation entering from this small opening, nothing comes out. It keeps on getting reflected within the pot. Hence, this small opening acts like an ideal black body. So let's start learning Stefan's law. If you have got a black body, assume a black body at temperature T. We know that every object above 0 Kelvin radiates, it gives out energy in the form of EM wave. So does the black body. Now, if you have a black body at temperature T, then the heat radiated in the form of EM wave by this particular black body is directly proportional to the surface area of the black body. So if you double the surface area, the heat radiated becomes double. If you triple the surface area, the heat radiated becomes triple. This is a question that gets asked. You have got two spheres. Same material, everything same. The first one is at temperature T. The second one is also at the same temperature T. The radius of first one is R. The radius of second one is 2R. If the heat radiated by the first one is Q, then what will be the heat radiated by the second one? So we know that for a sphere, the surface area is given by 4 pi r square. When the radius becomes double, as area is proportional to r square, the surface area becomes 4 times. So if the first sphere of radius r has a surface area A, then the second sphere of radius 2r will have a surface area 4a. And if the surface area will be 4 times, the heat radiated, the thermal power will be 4 times. So the energy radiated per unit time, Q, will be 4 times. So if the first one radiates Q, the second one will radiate 4Q. So what we need to understand, the first thing in Stefan's law, the heat radiated by a black body is directly proportional to its surface area. The more the surface area of the black body, the more heat will be radiated by it. The second thing, the heat radiated is directly proportional to the fourth power of absolute temperature. The heat radiated by the ideal black body will be directly proportional to the fourth power of absolute temperature. When I say absolute temperature, it means that the temperature has to be taken in Kelvin. A common error that students do, teachers give them question like initial temperature is 30 degrees centigrade, final is 60 degree centigrade. What happens to the heat radiated? Do not take the temperature in degree centigrade. Here you must substitute the temperature in Kelvin. Do not do this error. So the heat radiated is directly proportional to the fourth power of absolute temperature. So let's say if everything else is same, the surface area is same, radius is same, everything else is same. The first body is at 100 Kelvin. The second body is at 200 Kelvin. So the temperature is double. If the temperature is double, what happens to the heat radiated? So you say, sir, when the temperature will be double now, the heat radiated will be 2 raised to power of 4 times. Because heat radiated proportional to T raised to power of 4. That will be 16 times. So if the first body radiates energy per unit time equals to Q, then the second body will radiate 16 Q. Similarly, if let's say first body is at 200 Kelvin and second body is at 600 Kelvin, everything else same type of material, same surface area. If the first body radiates energy at the rate Q, the energy radiated per unit time is Q, then the second body, as you know that the heat radiated is proportional to T raised to power of 4. When the temperature becomes 3 times, the heat radiated becomes 3 raised to power of 4 times, and 3 raised to power of 4 is 81 times. So then the heat radiated will be 81 times. So if the first body radiates a heat Q, the second body radiates 81 Q. Similarly, bachon, if the temperature becomes 5 times, the heat radiated becomes 5 raised to power of 4 times, and 5 raised to power of 4 is 625 times. So keep this simple thing in mind. The heat radiated by a black body is directly proportional to the surface area. The greater the surface area, the more will be the heat radiated, and directly proportional to the fourth power of temperature. Now, what do physicists do every time they find a proportionality, sir? They add up a proportionality constant. So we write Q equals to sigma A T raised to power of 4. Here sigma is called the Stefan's constant. The value of Stefan's constant is 5.67 into 10 raised to power of minus 8. Easy to remember. Think like the dance step. 5, 6, 7, 8. 5, 6, 7, 8. Yeah, it comes out of 1, 2, 3, 4, but 5, 6, 7, 8. But no need to remember this. Why? Because this will be given in the paper. So no need to remember this thing. At your age, I never ever remember this. So Q equals to sigma A T raised to power of 4. A is the surface area. T is the temperature of the body on the absolute scale. Now here, what is Q? Sir, Q is the rate of flow of heat with respect to time. What is this big Q? Sir, heat, energy. And the rate of flow of energy with respect to time is called power. So beta, this Q is also called thermal power. Sir, in last class you said that this Q is called thermal current. Yeah, because there in conduction we were comparing it with current electricity, right? So thermal current, the rate of flow of heat. Here it is also rate of flow of heat, but here we talk in terms of power, the rate of flow of energy with respect to time. So now we will talk about Kirchhoff's law. If you have an object at thermal equilibrium, the power radiated by an object is equal to the power absorbed. So what is the meaning of thermal equilibrium? If there is an object at thermal equilibrium, it means that its temperature is neither increasing nor decreasing. And we know that every object above 0 Kelvin radiate. So this object at temperature T must be radiating. But we know that the temperature of this body is constant, just like everything in our real life. The things in your surrounding are constantly radiating, but their temperature do not change. Why? Because they absorb the same amount of energy from the surrounding as they are radiating, and that's why they maintain a thermal equilibrium. So at thermal equilibrium, the power radiated by an object is equal to power absorbed. Once the temperature becomes constant, then the power radiated has to be equal to power absorbed. Now, what does the Kirchhoff's law tells us? A very important statement that good absorbers are good emitters. Now, understand this. Let's say within your room, there is one particular object, let's call it object X. And this object X is at temperature T. So if this particular object X is at temperature T, it is above 0 Kelvin, yes. So it must be radiating. Now you can assume this object X to be either a good emitter or a bad emitter. Good emitter means that it emits lots of radiation, and bad emitter means it releases less amount of radiation. Now let's say I tell you this object X is a special type of object. It is a good emitter but a bad absorber. Can this happen? No. Why? Because I know that this object X in my room is in thermal equilibrium. And if it is in thermal equilibrium, its temperature is constant. If its temperature is constant, the amount of power emitted by it has to be equal to the amount of power absorbed by it. Hence, if it is a good emitter, it should be a good absorber so that it remains in thermal equilibrium. So that's why good emitters can't be bad absorbers. I have got one more argument to support this. Why a good emitter can't be a bad absorber? Because if something emits lot of energy but absorbs very less, it will constantly lose energy. And if it will constantly lose energy, its temperature will start to drop and eventually reach 0 Kelvin, and there is nothing in your room which is at 0 Kelvin. Reason being, there is nothing in your room which is a good emitter but a bad absorber. Now let's think of the counter case. Let's say you say that, sir, in my room I have a special thing. This is a bad emitter. It emits very less amount of radiation, but it absorbs a lot. So this is a bad emitter but a good absorber. Okay. Now this object absorbs all the radiation falling on it, but emits very, very less. So what will happen to the energy content of such an object? Sir, it's a bad emitter but a good absorber. It's a good absorber and a bad emitter. So its energy content will constantly increase and its temperature will continuously increase. And if its temperature will continuously increase over the period of time, it will reach infinite temperature. Hence, this case is also not possible. So a good emitter can't be a bad absorber. Eventually the temperature will become 0, and a bad emitter can't be good absorber because eventually the temperature will become infinity. So sir, what is true? A good emitter has to be good absorber and a bad emitter has to be bad absorber. So this can be explained using the thought experiments on bodies of different type, and the statement say, hence a good absorber has to be a good emitter. Sir, hence from where? From whatever I explained. A good absorber has to be a good emitter and a bad absorber has to be a bad emitter. Which is the most awesome absorber you know? So ideal black body. So the ideal black body has to be the most awesome emitter. For an ideal black body, we say that absorptivity is 1. So an ideal black body will have highest emission power, the highest emissivity we call it. But first we need to understand what is the definition of emissivity. So what the hell is emissivity? Emissivity, denoted by symbol E, has a definition, and the definition goes like: emissivity of an object is given by the power radiated by the object, by the body, upon the power radiated by an ideal black body of same surface area at same temperature. Now tell me, a black body has got high absorptivity, yes or no? Sir, it has the maximum absorptivity 1. And we have just learned that good absorbers are good emitters, yes. So can I say that a black body is the best emitter? Why? Because it's the best absorber. Now, we know that emissivity is the power radiated by the body upon the power radiated by ideal black body of same surface area at same temperature. If you have a body, let's say made up of plastic or something at temperature T, and you have got an identical, same shape, same size, black body at same temperature. Tell me, out of these two, which one is better absorber? Sir, ideal black body. So which one is better emitter? So black body. So I can say with guarantee that black body will radiate more compared to plastic or some other object. Yes. So if the heat radiated by the black body of same surface area at same temperature is QBB, and the heat radiated overall by this body is given by QB, then we say emissivity of this plastic is nothing but the heat radiated by the body upon the heat radiated by the ideal black body having the same surface area and being at the same temperature. So we can say that emissivity is nothing but power radiated by the body upon power radiated by an ideal black body of the same surface area at same temperature. And we know that the power radiated by this ideal black body is nothing but sigma a t raised to the power of 4. So bring this up and you will say power radiated by the body QB equals to E times the power radiated by black body of same surface area at same temperature. So from here you will say the heat radiated by any body will be equals to emissivity times sigma a t raised to the power of 4. Now this is the question asked. What is the emissivity of an ideal black body? So for black body, in place of body in the numerator you will write black body because you are finding the emissivity of black body, and since these two power radiated will be equal, the emissivity of an ideal black body is 1. So remember that beta, for an ideal black body absorptivity is 1, emissivity is 1, and it makes sense because good absorbers are good emitters. So the heat radiated by any object is equals to the emissivity of its material times sigma, which is the Stefan constant, times its surface area into the temperature raised to the power of 4. Now we will talk about something called the rate of cooling. Now if you have a spherical object of radius r, what is the rate of cooling? You know that if this object is at temperature T, it will radiate. Yes. And if you place it in vacuum, there is no surrounding, it can't absorb. In vacuum, it will just keep on radiating. So what will be the rate of decrease of temperature of such an object if placed in vacuum? So I need to find the rate of cooling. Okay. So how to find it? See beta. You know that the heat radiated will be equals to sigma E A t raised to the power of 4. What is sigma? Stefan constant. What is E? Emissivity of this object. A, the surface area, into t raised to the power of 4. Now what is Q? So the rate of flow of heat. So in place of Q, the thermal power, you can write dQ by dt. And in place of surface area, you can write 4 pi r square. So sigma E into 4 pi r square into t raised to the power of 4. So why you wrote the surface area as 4 pi r square? Because I have specified this is a spherical object. Now, our mission is not to find the power radiated. Our mission is to find the rate of cooling, which is dt by dt. So we play a smart trick here. We say that the infinitely small heat given has to be equals to ms dt, q equals to ms delta t. So dq equals to ms dt. So in place of beta dq, write ms dt by dt equals to sigma e 4 pi r square into t raised to the power of 4, the fourth power of absolute temperature. Now in place of mass of this sphere, you can write density of sphere into volume. The density of sphere, let's say rho, and the volume is 4 by 3 pi r cube. So once you substitute it, the left hand side becomes density into 4 by 3 pi r cube, that is mass, into the specific heat into the dt by dt. So what is this dt by dt? This dt by dt is the rate of change of temperature with respect to time. This dt by dt is the rate of cooling when you place a spherical object in vacuum. It will keep on radiating and it will keep on getting cooled. So you can say density into volume into specific heat into the rate of cooling equals to, on the right hand side, sigma e 4 pi r square t raised to the power of 4. Our mission here is to find the rate of cooling depends upon which power of radius. So you will say on the left hand side r cube into dt by dt is proportional to, on the right hand side, r square. So you can say dt by dt, the rate of change of temperature with respect to time, is proportional to 1 by r. So the rate of change of temperature with respect to time is proportional to 1 by r. It means that if you have got two spheres, one big and one small, one with smaller radius will cool down faster. And we apply this knowledge in our everyday life. Let's say we are eating rice which has been just cooked, and if we have on our plate the heap of rice and we want to eat quickly, what do? We take a small part and spread it, right? Spreading, we increase the surface area. Smaller radius cools down faster. So if you have a whole blob of hot steamed rice, and only small grain, then the small grain will have a smaller radius and hence it will cool down faster. So remember that the rate of cooling is inversely proportional to radius. So greater the radius, the slower the rate of cooling, the smaller the radius, the faster the body cools down. So hence we can say the power radiated is proportional to r square for a spherical object. Why? Because sir, the surface area is 4 pi r square. So the power radiated, which is directly proportional to surface area, is directly proportional to r square. Here you can see the power radiated dq by dt is proportional to r square. While the rate of cooling is inversely proportional to r. So you have to remember these two things for a spherical object. Now let's practice a question based on the same thing. Let's say here you have got two spheres. Both are placed in vacuum. The first one has radius r, the second one has radius 2r, and both are made up of same material and at same temperature. So if both the spheres are made up of same material and are at same temperature, then what is the ratio of heat dissipated and the ratio of rate of cooling? So what will be the ratio of thermal power and what will be the ratio of rate of cooling? So you will say the power radiated is directly proportional to area is directly proportional to r square. If you take the power radiated by first one as q1 and second one as q2, then you can say that q1 by q2 equals to area 1 by area of 2 equals to radius of 1 by radius of 2 whole square. So you will say q1 by q2 equals to radius of 1 r by the radius of second one 2r whole square. So you get q1 by q2 equals to 1 by 4, or q1 by q2 equals to 1 by 4. So q2 has to be equals to 4 times of q1. And isn't this obvious, sir? The second one has double the radius, huh? So 4 times the surface area. If 4 times the surface area, the power radiated by second one has to be 4 times of the power radiated by first one, right? Moving on. Now, if we talk about the rate of cooling, we know that the rate of cooling, the rate of drop of temperature is inversely proportional to radius. The second sphere has double the radius, so its rate of cooling will be half. End of discussion. Or we can say dt by dt proportional to 1 by r. So you will say the rate of change of temperature of first object with respect to time upon the rate of change of temperature of second object with respect to time equals to r2 by r1, and r2 by r1 will be 2r by r. So cancel out rr. On the right hand side you get a 2. Hence you will say the rate of cooling of the first object is 2 times the rate of cooling of the second object. The rate of cooling of the first object will be double that of the rate of cooling of second object. Okay. So now we are going to discuss the spectral energy density curve. What does it mean? Let's see. We have learned that every object above 0 Kelvin radiates. Yes. So let's say there is one object at temperature T. It will radiate EM waves. Okay, sir. Now question is, it will radiate which type of photon? It will radiate, X-ray, gamma ray, visible. Which type of photon? So sir, it will radiate which type of photon? If I turn the light in my room off, I can't see majority of objects. Why? Because the type of radiation they are producing are not at all visible. So this means that all of them produce only infrared radiation, which I can't see, or they produce micro or radio. I know as a matter of fact, they do not produce lot of UV, X-ray and gamma ray because those causes mutation. So if they will be, producing UV, X-ray, gamma ray, then I would have got cancer by now. So that is not at all case. So they must be producing infrared or radio or micro. But question is, which one? So the answer is they just do not produce any one particular wavelength. They produce all wavelengths. So every object emit out all wavelengths. But there is a particular wavelength which dominates, which has got maximum energy associated with it. So if we look at the distribution of the intensity associated with a particular wavelength versus the wavelength, we say that all object above 0 Kelvin radiates, and they radiate all possible type of wavelengths. But there is a particular wavelength corresponding to which the intensity is maximum, and this particular wavelength is called lambda max. Lambda max doesn't mean that wavelength is maximum. Lambda max means that this is the particular wavelength associated with which energy radiated is maximum. Now beta, remember that lower wavelength means more energetic photon. Lower wavelength take you towards gamma. Okay, and higher wavelength means less energy. Higher wavelength takes you towards radio. So if you have got any object above 0 Kelvin, it radiates. Which type of wavelength? All possible types. But there is a particular wavelength that dominates, and this particular wavelength corresponding to which maximum intensity is observed, that is called lambda max. Do remember the area under this graph. The area under this graph is directly proportional to the total power radiated. Total power radiated. So the area under this graph is proportional to the fourth power of temperature, and the area under this graph is proportional to the surface area of the object making the radiation. So remember that the area is directly proportional to the total power radiated. So what does this graph represent? It shows with any particular wavelength what is the intensity of the radiation being produced. Every object produces radiation of all possible wavelengths. So this brings us to Wien's displacement law. What does the law say? Lambda max is inversely proportional to the absolute temperature. So if the temperature becomes double, lambda max becomes half. Temperature becomes triple, lambda max becomes 1/3. Isn't this obvious that if you increase the temperature of an object, it will release out photons of even higher energy? And when I have drawn the spectral energy distribution curve, I said that there is a particular wavelength corresponding to which the intensity of radiation is maximum. When you heat up the object, the photons coming out becomes more energetic. So the lambda max decreases, and this is the basic idea of Wien's displacement law. So the lambda, the particular wavelength corresponding to which you have got most of the intensity associated, that is inversely proportional to the absolute temperature. Or you can write lambda max into T equals to constant, and the value of this constant is equals to 2.89 into 10 raised to the power of -3 meter Kelvin. Unit of wavelength meter, unit of temperature Kelvin, so meter Kelvin. So do we need to remember this? No, do not worry. Now, if you have plotted the graph for a particular temperature, let's say T1, then for a higher temperature, if beta temperature increases, the radiation increases, right? And we know that radiation is proportional to the fourth power of temperature. So if you increase the temperature, what happens to lambda max? So the lambda max decreases, as well as the overall radiation increases. So the area under the graph should increase and the lambda max should decrease. So if you think of the graph at a particular temperature and then visualize the graph at a higher temperature, the graph goes something like this. So at a higher temperature, the lambda max is less, but the area under the graph is more. Why? Because the power radiated will be more. So here you can say, since for this second graph, which is drawn at temperature T2, the lambda max is less, I can say that T2 has to be greater than T1, and that's why the lambda max 1 is greater than lambda max 2, or the lambda max 2 is less than the lambda max 1. Now this is the basic thing on which question comes most of the time in NEET, a simple argument that lambda max into T is constant. If you increase the temperature on the absolute scale, the lambda max decreases. Now which type of question get asked here? They will say, for two objects, the particular wavelength for which the intensity is maximum are given by lambda and 2 lambda. If both the objects are identical, what is the ratio of their power dissipated? So you will say the second one has got wavelength double, yes. So its temperature will be half. Why? Because lambda max into T is constant. So if the first one has temperature T, the second one will have temperature T by 2. And we know that heat radiated is proportional to temperature raised to the power of 4. Since second one has half the temperature, it will have 1/16 the power dissipated. So if first one dissipate out a thermal radiation of power Q, The second one will radiate out Q by 16. So these type of questions do come. Just remember this simple law, lambda max into T equals to constant. Now sometimes we have to deal with small changes. So we know that lambda T equals to constant. For small changes we can write delta lambda by lambda plus delta T by T equals to 0. You can bring this delta T by T to the right hand side and write delta lambda by lambda equals to minus delta T by T. So the fractional change in wavelength equals to minus times the fractional change in temperature, given that you are taking the temperature on the absolute scale. The fractional change in wavelength equals to minus times the fractional change in temperature. Better do remember this thing works only for small changes because we have used the small change formula here. Now, important points that you should know about Wien's displacement law. First, better take temperature in Kelvin. Take the temperature on the absolute scale. I have seen students doing this wrong all the time. They keep on playing in degree centigrade. Do not do it. Please convert the temperature from degree centigrade to Kelvin. Second, as the temperature increases, the body's spectrum shift towards lower wavelength. I have just shown you this graph. If let's say this is the graph at temperature T1 and this is the graph at temperature T2, then as the temperature increases, the wavelength decreases, right? The wavelength decreases, the energy of the photons increases. So as the temperature increases, the body's spectrum shift towards a lower wavelength. But what is the meaning of shifting of spectrum? We know that infrared has got less energy than visible and visible has got less energy than ultraviolet. Rather than writing visible, I am breaking it down into the visible colors. So we have got infrared, then we have got VIBGYOR, and then more energy than the violet, we have got ultraviolet. Now, when I say that on heating the object, the temperature increases, the lambda decreases. Going from left to right, beta, the energy increases, the lambda decreases. So the spectrum shift towards lower wavelength. Now, if we have got any metal object in our room, it is giving radiation with dominance in the infrared region. If you heat it up, I can promise you, despite the type of metal, the first color you see on heating it, the first color it emits when it starts glowing is red. Why? Because on heating, the spectrum shifts towards the lower wavelength. So as the spectrum shifts, the first visible color that gets into the spectrum is red. That's why every object which when it starts emitting, the first color you see is red. If you keep on further heating, the spectrum shifts further and then more colors from the spectrum gets in and the mixture of this red, orange, yellow and green appears to be yellowish. You heat it further, more colors from the spectrum get in, it shifts more towards right and it contains the entire visible spectrum and then it appears white. If you heat it further, the spectrum keeps on shifting towards the lower wavelength and as it keeps on shifting, red, orange and yellow will go out of the spectrum and then you will see a blue color and there will be some part of ultraviolet, but that is something you won't be able to see. So what I'm saying here is hence on heating a body, the color changes from first color you see is red, then you see yellow, then you see mixture of all the visible which is white, then you see violet or blue types of colors. So hence on heating an object, the color changes from red to yellow to white and then to blue. You might have heard of this term blue star. Our sun is a white star. But a blue star have got higher energy than those of white star. Blue stars are at higher temperature than the white star. So remember that, hence a blue star is at higher temperature than the white star because their spectrum is shifted towards even lower wavelength or towards even the wavelength corresponding to higher energy. So let's move on and now talk about the net power loss. Let's say you have got 10 object at temperature T placed in a surrounding at temperature Ts. Now this object will emit radiation. Why? Because it is above 0 Kelvin and this will even absorb radiation from the surrounding. You will say that the heat radiated will be equals to sigma E8 T raised to power of 4, where E is the emissivity of this material and T is its temperature. while it will even absorb radiation from the surrounding, and that absorbed power, the energy absorbed per second, is given by sigma EA temperature of surrounding raised to the power of 4. Now here, technically we should write absorptivity, but we have taken absorptivity same as the emissivity because we know that good absorbers are good emitter and bad absorbers are bad emitter. So you get sigma EAT temperature of surrounding raised to power of 4. Now what will be the net power loss? The net power loss will be emitted minus absorbed. So you will say the heat exchange net equals to sigma EA common T raised to power of 4 minus Ts raised to power of 4. Temperature of body raised to power of 4 minus temperature of surrounding raised to power of 4. And this particular idea is important because this is the father of Newton's law of cooling. How? Let's see. So now let's talk about Newton's law of cooling. Let's say we have a body placed in a surrounding. The surrounding temperature is Ts and the body has got slightly different temperature than the surrounding. Let's say the temperature of this body is delta T higher than the temperature of surrounding. Then you will write the temperature of this body to be temperature of surrounding plus delta T. It is delta T higher than the temperature of surrounding. We will say that the net rate of heat loss will be equals to sigma EA temperature of body raised to power of 4 minus temperature of surrounding raised to power of 4. So sigma EA Ts plus delta T, if there is a temperature difference delta T between the surrounding and the body, sigma EA Ts plus delta T raised to power of 4 minus Ts raised to power of 4. From these two terms, if you take Ts temperature of surrounding raised to power of 4 common, what do you get? Sigma EA into temperature of surrounding raised to power of 4. Now from here, temperature of surrounding plus delta T. If you take the temperature of surrounding outside, you get 1 plus delta T by Ts raised to power of 4 minus temperature of surrounding raised to power of 4 has been taken out, it will be 1. Pause the video and look at this particular step if you are finding doubt. Now, if beta, the temperature difference upon temperature of surrounding is less than 1. If the temperature difference between the body and surrounding is less than the temperature of surrounding. Beta, do remember here we should take the temperatures in Kelvin. So if the, let's say, temperature of this body is 274 Kelvin and temperature of surrounding is 273 Kelvin. Okay, then there is a temperature difference of 1 Kelvin. There is a temperature difference of 1 Kelvin and temperature of surrounding is 273. So now here, if delta T by Ts is less than 1, we can do binomial approximation and bring this 4 here. So this becomes sigma EA temperature of surrounding raised to power of 4 whole times 1 plus 4 delta T by Ts minus 1. These two beta 1 get cancelled. So what you get is sigma EA temperature of surrounding raised to power of 4 into 4 delta T by temperature of surrounding. You cancel it here, you get a cube. So the net rate of heat flow equals to 4 sigma EA temperature of surrounding whole cube into delta T. But what we need to focus here is on this small part. The net rate of heat flow is directly proportional to the temperature difference. Hence, the net rate of heat flow is directly proportional to the temperature difference. The net rate of heat flow is directly proportional to the temperature difference. From where did we get the Newton's law of cooling? From the radiation mode of heat transfer. And remember this simple line, the net rate of heat flow is directly proportional to the temperature difference. Before we do some numerical on it, let's think of two theoretical questions. The first one coming right up. When a cup of tea is prepared, its temperature is 100 degrees centigrade and it is placed in a surrounding of 30 degrees centigrade. So you make a cup of tea, the temperature of this cup is 100 degrees centigrade and it is placed in a surrounding of 30 degrees centigrade. If the time taken for the temperature to drop from 100 to 90 is T1 and time taken for temperature to drop from 90 to 80 is T2, compare T1 and T2. So you have made a cup of tea at 100 degrees centigrade. The surrounding is at 30 degrees centigrade. As the cup of tea cools down, it won't happen that surrounding will heat up because surrounding is way bigger than the cup of tea. So now they are saying the temperature drops from 100 to 90 in a time T1 and then from 90 to 80 in a time T2. So they are asking you which time will be more. Now this is a simple question and the only line you need to solve this particular question is that the rate of heat flow is directly proportional to the temperature difference. When the body is hotter, the temperature difference is higher. So the rate of heat flow is higher. As the body starts to cool down, the temperature difference starts to decrease. So now the rate of heat flow will decrease. For the same temperature drop, same magnitude of temperature drop from 100 to 90 and from 90 to 80, from Q equals to mass of T into specific heat of T into delta T, we can say that, sir, for same amount of temperature drop, the same amount of heat should flow out. But as the temperature difference between the body and surrounding is continuously decreasing, the Q is decreasing. So you want the same amount of heat to flow out to reduce the temperature from 90 to 80 as to reduce the temperature from 100 to 90. But as the body cools down, the temperature difference decreases, the rate of heat flow decreases. So it will take more time for same amount of heat to flow. Hence, I can say this time taken T2 will be more than T1 because initially the temperature difference is higher. So the rate of heat flow will be higher. So the time taken will be less. Hence, I can say T2 has to be greater than T1. So as we know, the rate of heat flow is directly proportional to temperature difference. Hence, when the temperature decreases from 90 to 80, the average temperature difference with the surrounding is less. So the time taken is more. That's why beta T2 will be greater than T1. One more theoretical question based on Newton's law of cooling before we move on to the numerical. A fresh cup of tea is prepared at 100 degrees centigrade and kept in a surrounding at temperature of 30 degrees centigrade. If the temperature at time equals to 10 minutes, in 10 minutes the temperature of the cup of tea has dropped from 100 to 90. Then the temperature at time equals to 20 minutes. It means after next 10 minutes, the temperature will be more or less than 80 degrees centigrade. So you need to answer this question. Okay, so when this cup of tea is prepared at time equals to 0, its temperature is 100, the surrounding is at 30. At time equals to 10 minutes, you are saying that the temperature has dropped from 100 and is now 90 degrees centigrade. So then at time equals to 20 minutes, that in another time frame of 10 minutes, the final temperature will be found to be more than 80 or less than 80. What will be the final temperature? That's what you are trying to ask. It will be more than 80 or less than 80. The answer is more than 80. Why, sir? Why? Listen. Sir, initially temperature difference is more. Yes. So the rate of heat flow from the cup of tea to the surrounding will be more. So in 10 minutes, more amount of heat would have transferred. In the next 10 minutes, since now the temperature difference between the body and the surrounding is decreasing, the rate of heat flow will decrease. So in the same amount of time, the lesser amount of heat will flow. If in the same amount of time, lesser amount of heat will flow, I will say the lesser temperature will decrease. So if in the first 10 minutes, temperature decreased by 10 degrees centigrade, in the next 10 minutes, it will decrease by amount less than 10. So it will decrease by, let's say, 7 degrees centigrade or 8 degrees centigrade. And the final answer will be more than 80. So as the temperature difference decreases, so is the rate of flow of heat. So in the same time, lesser amount of heat is released. Hence the final temperature will be more than 80 degrees centigrade. Okay. Moving on. Now let's do numerical. How to solve question based on Newton's law of cooling. So let's say there is an object which is initially at temperature Ti and it cools down to a final temperature Tf in a surrounding at temperature Ts. Listen carefully. Initial temperature Ti, final temperature Tf, temperature final, and cooling in a surrounding of temperature Ts. You will say the heat flow rate is directly proportional to the temperature difference. But sir, which temperature difference? As the body cools down, its temperature difference with the surrounding continuously changes. Initially, the temperature difference was Ti minus Ts. Finally, the temperature difference is Tf minus Ts. Then which temperature difference should I take? I am saying that the rate of heat flow is directly proportional to the temperature difference between the body and the surrounding. But sir, the temperature difference continuously changes. So which temperature difference should I consider? Average. The initial temperature difference will be beta Ti minus Ts. The final temperature difference will be Tf minus Ts. So what will be the average temperature difference? So you will say the initial temperature difference plus the final temperature difference by 2. That will be Ti minus Ts, the initial temperature difference, plus final temperature difference, Tf minus Ts by 2. This is how we take the temperature difference. So we say that the rate of heat flow is directly proportional to the average temperature difference. The average temperature of this body will be initial temperature plus final temperature by 2 minus the temperature of surrounding. So this is the average temperature difference. So you just did Ti minus Ts plus Tf minus Ts by 2. Beta same thing, na? Take Ti and Tf together. So you get Ti plus Tf, the initial plus final temperature of the body by 2 minus 2 Ts by 2. That is minus Ts. Okay, so the rate of heat flow is directly proportional to the average temperature difference. Now, since we know proportionality, what do? We place a proportionality constant. So here we say the rate of heat flow equals to K times the average temperature difference. Now this Q represents what? Sir, the rate of heat flow. So the total heat flow upon the total time taken. No? And you can write the total heat flow as mass times specific heat times delta T upon T. So you can write ms delta T by T. The rate of heat flow equals to some proportionality constant times the average temperature difference. And this is something which I am going to use to solve all the question. So ms delta T upon the time taken for that heat transfer equals to K times the average temperature difference between the body and the surrounding. So let's see a simple numerical based on this. Numerical goes like, a solution cools from 40 degrees centigrade to 30 degrees centigrade in a surrounding of 25 degrees centigrade in 10 minutes. So cool down from 40 to 30 in a surrounding of 25 degrees centigrade in 10 minutes. Determine the time taken for the temperature to decrease from 30 to 27.5. So if it cools from 40 to 30 in a surrounding of temperature 25 in 10 minutes, determine the time taken by it for the temperature to decrease from 30 to 27.5. Beta, do not worry about all these questions, what it says. Just focus that there will be one formula used. What? The rate of heat flow is directly proportional to temperature difference. Here the temperature keeps on changing, so we say the rate of heat flow is directly proportional to the average temperature difference, that is T initial plus T final by 2 minus temperature of surrounding. So then we need to place a proportionality constant, and in place of Q write M as delta T by T. Game over every time. So I'm going to use this here. How? Let's see. The body cools from 40 to 30. Let's say the mass of the body is M, specific heat S, and the temperature drop is 10. In how much time, bachcho? 10 minutes. And you can write the average temperature difference between the body and surrounding. As the temperature of body decreases from 40 to 30, the average temperature of the body will be 40 plus 30 by 2. That is 35. So the average temperature difference between the body and surrounding will be 35 minus 25. That will be 10. So you can write, as the body cools down from 40 to 30 in a surrounding of temperature 25, and they are asking you what will be the time taken as the body cools down from 30 to 27.5 in the surrounding of 25. So for the first case, you will say mass times specific heat times delta T from 40 to 30, 10 upon the time taken, beta. 10 minutes. I have kept here in minutes so that I will get the final answer also in minutes. Do not worry that why sir have not converted from minute into second. So this is the rate of heat flow. This has to be equals to a proportionality constant times the average temperature difference. Sir, how do you know that average temperature difference is 10? Easy. Initial temperature 40. Final temperature 30. So the average temperature will be 40 plus 30 by 2. That is 35. So the average temperature difference between the body and surrounding will be 35 minus 25. That is 10. That's why I have written 10 here. Our mission is to find the time taken for the temperature to decrease from 30 to 27.5. As the body cools down from 30 to 27.5, the drop in temperature is 2.5. So write ms into 2.5 upon the time taken, which we need to find, equals to T, equals to K times the average temperature difference. Now what will be the average temperature difference in this case? So you write 30 plus 27.5 by 2 minus 25. 30 plus 27.5 gives you 57.5 minus 50 by 2. Take this also. So you will get 7.5 by 2. So equals to k into 7.5 by 2. Once you have written this, game over. Now bachcho, divided both the side. ms k. And this 10 becomes 1. So you get 1 upon 2.5 by t equals to, on the right hand side you will get 10 upon 7.5 by 2. So you get t upon 2.5 equals to 20 upon 7.5, right? So on dividing, you will get t upon 2.5 equals to 20 upon 7.5. Cancel out 2.5. 7.5 is 3 times of 2.5. So place here a 3. So the time taken will be 20 by 3 minutes. So now we are going to understand the graphs of Newton's law of cooling. But before we learn the graph, we are going to understand the equation. Do not worry about the equation. You have to focus on graph. So let's say we have a body at temperature T placed in a surrounding at temperature Ts. We say the rate of heat flow equals to some proportionality constant times the temperature difference. So Q equals to some proportionality constant times the temperature difference between the body and surrounding T minus Ts. You can write this, the rate of heat flow, as dQ by dt. And you can write dQ, the infinitely small heat flow, equals to mass into specific heat times the infinitely small change in temperature upon dt. So you can write ms dt by dt equals to k into T minus Ts. Technically, this equation is not correct. Why? Because here the heat flows from the body. When heat is given to the body, it is taken as positive. When the heat flows out of the body, it is taken as negative. So technically, there has to be a minus sign here. Now, you can bring the term of temperature on one side and write dt upon T minus Ts equals to minus k by ms into dt. So you get dt upon T minus Ts equals to minus k by ms into dt. Integrating both the side, on the left hand side from initial temperature Ti to final temperature Tf, and on the right hand side from initial time 0 to final time t. Now once you have integrated, integration of this part is something which students find difficult, and we have learned that integral dx upon ax plus b is given by ln of ax plus b by a. Here the coefficient of t is 1, so in the end you have to divide with 1, and here the b, the quantity which gets added with the variable, that is minus ts. So this integration is not tough, it's just that you have not memorized it. So when you integrate it now, you get integral of dt upon T minus Ts to be simply equals to ln T minus Ts. That's easy. So ln T minus Ts, lower limit Ti, upper limit Tf equals to minus k by ms times integral of dt, that gives you the time. Now always substitute bachcho upper limit minus lower limit. So you will get ln Tf minus Ts minus ln Ti minus Ts equals to minus kt by ms. Ln A minus ln B can be written as ln of A by B. So here you will write ln Tf minus Ts upon Ti minus Ts equals to minus k by ms into t. Now what is Tf minus Ts? The final temperature difference between the body and surrounding. What is Ti minus Ts? The initial temperature difference between the body and the surrounding. So bachcho, you can even write ln of the final temperature difference upon the initial temperature difference equals to minus k by ms into t. Now if we know that ln A equals to B, then A can also be written as e raised to power of B. So using the same thing, you can say the final temperature difference upon initial temperature difference equals to e raised to power of minus kt by ms. Or you can bring this t initial towards the right and write the final temperature difference. The temperature difference between the body and surrounding at any time t equals to initial temperature difference into e raised to power of minus kt by ms. Now what I tell students here, this is same as nuclear. The number of active nuclei at any time t equals to initial number of active nuclei e raised to power of minus lambda t. Here beta, the temperature difference between the body and surrounding at any time t equals to initial temperature difference into e raised to power of minus some constant into t, and here the constant is minus k by ms. You do not need to remember this thing. Just remember that just like in nuclear decay, the number of active nuclei keep on decaying with time, initially n naught, and then they drop to 0 eventually. Here beta, the temperature difference between the body and surrounding decays in the same way. So we are focusing on the graph. Keep focusing. Remember this equation. The temperature difference between the body and surrounding at any time t equals to initial temperature difference into e raised to power of minus something into t. So what does the graph look like? So we know that the final temperature difference equals to initial temperature difference into e raised to power of minus something into t. So when we plot the graph of temperature difference between the body and surrounding versus time, we get the graph same as that we get in nuclear. So the temperature difference drops from initial temperature difference to finally zero. And doesn't it make sense? If I make a cup of tea at, let's say, at 100 degrees centigrade and place it in a room at 30 degrees centigrade, I ask you what is the initial temperature difference? You will say 70 degrees centigrade. 100 minus 30. I ask you what is going to be the ultimate final temperature difference. You will say, sir, over the period of time, this tea will keep on cooling, and finally it is going to have the same temperature as the surrounding. So I ask you what will be the final temperature difference between the tea and the surrounding. You will say, sir, zero. Finally it is zero. So the graph goes from initial to the final, and it goes same as that of nuclear decay. But many a time they don't ask you the graph of temperature difference between the body and surrounding. They ask you the graph of temperature of the body. So you will say final temperature of the body minus temperature of the surrounding, which is nothing but the final temperature difference, equals to initial temperature difference into e raised to power of minus kT by ms. So you will say the final temperature of the body, the temperature of the body ultimately equals to initial temperature difference into e raised to power of minus kT by ms plus ts. So what is the difference between this? If I tell you that I have made a cup of tea at 100 degrees centigrade and I have placed it in a surrounding at 30, I ask you what will be the final temperature of the tea. It won't be zero. No. The final temperature of the tea will be same as the temperature of the surrounding once it attains thermal equilibrium. The initial temperature difference will be 70. The final temperature difference will be 0. The initial temperature is 100 and the final temperature will be same as that of temperature of surrounding. So when we plot the graph of temperature of the body versus time, so we say that the final temperature is not 0. The final temperature of the body is not 0. The ultimate temperature of the body is same as the temperature of surrounding. So you should know these two graphs as well in Newton's law of cooling. So that's all in our radiation part. In the next hour, we will talk about calorimetry. See you guys there. Bye bye.